I'll do 7 ways a black hole can kill you. It used to be 10 ways a black hole can kill you. There have been NASA cutbacks and things like that. So, in fact, finding just 7, there are actually many more. There are other ways of talking about it, but it turns out there are different ways a black hole can kill you. First of all, what is a black hole? Well, NASA has a picture of one. Here you go. Excuse me. There it is. There it is. It's not to scale. Oh, it shouldn't be showing my mouse. What's it doing? That's interesting. How do I do that?
It's caught in the event horizon.
That's interesting, yeah. There has been a black hole found on Earth. I don't know if you've heard of this place. It's out. I think it's out in California. It's a junk shop. They sell all kinds of stuff. I would make the New Delhi joke, but this is a lot better. People have a lot of bad ideas about what a black hole is. Science fiction authors, you probably know about how they form the core of a supernova and that sort of thing. But in fact, you can have a black hole without involving that at all. There's a definition of what a black hole is, and that is, evidently everything is totally freaking out. It's a place where the escape velocity is faster than the speed of light. That's really all it is. It could be anything. As long as the escape velocity is faster than the speed of light, you've got yourself a black hole. Well, what does that mean? Have you gone over escape velocity yet?
More or less.
More or less. Okay, well, it's not that hard of a concept, actually. Basically, if you have an object with mass, it has gravity. And if it has gravity, then you can take an object, like a remote control for a projector, probably a bad idea during a talk to fiddle with this. But if I give this thing energy in the form of velocity, it goes up a certain distance, but gravity's pulling it down, slows it down, it stops, and falls back. If I give it more energy in the form of more velocity, it'll get up higher. And it'll get up higher and higher the more energy, the more velocity I give it. In fact, as it's getting higher, the gravity from the Earth is getting weaker. Right? The force of gravity depends on your distance from an object. So the higher up this thing gets, the less gravity is pulling on it. And I actually have a description of this. So that basically, if you toss something up hard enough, the gravity of the object, gravity of the Earth, say, is always slowing it down. But if the object is moving fast enough, the Earth can't slow it down enough before it can escape forever. That distance, that speed that you throw it at, so that Earth's gravity slows it continuously until at infinity it stops, is the escape velocity. It's not a real thing. It's more of a concept than an actual physical process. It's a limit. For the Earth, it's 7 miles per second. If you throw something slower than 7 miles per second, it'll go up and come back down. The faster you throw it, the higher it'll go. If you throw it faster than 7 miles per second, it'll just escape, gone. And even when it's passing Pluto or the nearest star, it still has some positive velocity. If you throw it right at escape velocity, for the Earth 7 miles per second, 11 kilometers per second, it will always slow but never quite stop. It's always slowing, 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 slowing. When it gets to the edge of the universe, it will stop. Take that with a grain of salt as you wish. So the escape velocity depends on the gravity of an object. Well, what does gravity depend on? Well, what does gravity depend on? What is this machine doing to me? Here we go. Hang on, something screwed up. I think I skipped a slide. I'm having all sorts of issues here. You know what? I'm just going to run with it. Here we go. All right. The gravity of an object depends on 2 things. It depends on the mass of the object, and it depends on your distance from it. So, for example, if I take an object with low mass, it has low gravity. If I throw a ball up in the air, it goes way up. If I increase the mass, keeping the size the same, I just make it denser, then the object won't go up as high and it'll fall back down. And this will increase for higher and higher mass. Eventually, I can squeeze enough mass into this object that the escape velocity will reach the speed of light. And when it does that, you could shine a flashlight on this thing and the light will go up and come back down. Not really. That's a cartoon, but you get the point. Even light cannot escape because the escape velocity is faster than light. There's another way to do this. I can keep the mass the same, but decrease the radius of the object. The force of gravity depends on how much mass you have, but also how big the object is. What Newton showed hundreds of years ago using the calculus, which is not on the back of my shirt, what it really depends on is your distance from the center of the mass of the object. If you're standing on the surface of a sphere, it makes no difference if that mass is evenly distributed in the sphere or if it's all condensed at one point right at the center. Mathematically, it makes no difference. So what you can do is you can start keeping the mass the same but decreasing the size of the object. Your distance from the center decreases, and so the force of gravity increases, and eventually again you get to an object that is so small that the gravity makes the escape velocity faster than light, and you have a black hole. So the question now is, what is a black hole? We can answer that a little more specifically. It's an object with a high enough mass or a small enough radius, or in fact both, such that at the surface the escape velocity is faster than light. Nothing can escape. So that brings us to the first way a black hole can kill you. And now I realize why I'm missing a slide, because I gave this talk in the public and I had the equation for gravity in it and I took it out. So I should have put it back in. I just realized that. Sorry about that. But now we come to the first way a black hole can kill you, and that is very simply falling in. I don't know if you saw that before. Yeah, okay. Honestly, if you have a black hole, the escape velocity is faster than light. If you fall in, you're stuck. You're dead. You can't get back out. You fall in, bloop, you're gone. And so you're down the drain, and that's it. Now, I do want to say, I love this cartoon. I found it on the web, and I wish I could find a better example of it, but this was back when the web was very young. I think I downloaded this with Mosaic, so it's gone. Those electrons have actually decayed into nothing by now. You've probably seen these diagrams, these two-dimensional diagrams of space-time grid, where you have this big funnel shape and they drop down in there. This simple diagram has caused more misconceptions among people. This makes me crazy. You're taking the three-dimensional volume of space and collapsing it down in one dimension, and then saying gravity is sort of like warping it into another dimension. This is a fine analogy. You can talk about bed sheets and putting a bowling ball in the bed sheet and how it dips it and all that stuff. The problem is this makes people think about space two-dimensionally. I have kids who come up to me and say, well, you can't escape a black hole, but what if you come up from the other side? Right? So they think you're down here, but what if you come from this direction, or from here? It's like, but there's no there, right? In three-dimensional space, the black hole forms a sphere. And so there's no way you can approach it that you're not hitting that region of space where the escape velocity is greater than light. And now I'll prove myself a liar, because now I see the next slide. I actually do put in the equation. I evidently rearranged this talk. I'll just go back and retcon this whole thing and say, oh yes, this slide, I moved it later. So again, the force of gravity depends on the mass of the object and your distance from it. This is Newton's equation for the force of gravity. I don't know if you're all familiar with this, but it's relatively simple. You've got a number which is g, and it's just a number. It's a very small number, but it's a number. The mass of one object, the mass of a second object. So the force of gravity depends on how massive these two objects are, divided by the square of the distance between them. This is actually the force of gravity. So the Earth has a force on you, and that force is equal to your weight. Right? Your mass, my mass, is about 75 kilograms. That doesn't change whether I'm in space or not. That's an intrinsic property of being me. But if I'm standing on the Earth, then my mass is being pulled by the mass of the Earth, and that force becomes my weight. When I go to the moon, right, the moon has a different mass, a different radius of the Earth. My mass stays the same, but the mass of the moon is different, r is different, and when you do all the numbers, you would weigh a sixth as much on the moon as you do on the Earth, even though your mass is the same. Going right past this. So the thing about gravity is, if you're really close to an object, or it's really massive, that force becomes very strong. Now on the Earth, you can't get any closer to it than we are now. Well, you could be at sea level, 7,600 feet or whatever it is, closer to the center of the Earth. But if the Earth were a perfect sphere, then the surface of it would be as close as you could get to it. But really, remember, we're talking about what Newton said, and that is, it's your distance to the center of the object that's important. So if I were to crush the Earth and make it smaller, even though the mass is the same, the radius is lower, right? I've said this before, the gravity would increase. So you can get closer to the Earth by getting closer to the center of the Earth. If you dug down into the Earth, it's different, because now there's mass above you, and that gets complicated. I won't get into that. So this only works if you're actually crushing an object. The deal about black holes is that they can be really massive, but they're really small. So you have a lot of mass, and you can get really, really close to them. And that actually brings us to the second way black holes can kill you, and you probably know about this. Let me describe it. The force of gravity from an object changes, as I said earlier as well, as you get closer or farther away from it. Well, let's take our object, let's call it a black hole. Let's put a little sphere at some distance from it, and we'll measure the force on it from the center of the sphere. And there's some force on the sphere as it's falling towards the black hole. The force of the black hole is gravity. As it gets closer, that force gets greater. And as it gets really close, that force gets really great. Hey, but wait a second. Something closer to a black hole feels more force. Let's zoom in on this, and let's look at our object again. But you know what? This object has two sides. It has a near side and a far side as far as the black hole is concerned. And it has a center. The center feels one force, but the far side here feels a smaller force. It's farther away from the black hole. Maybe not a lot farther, but a little bit. And the near side of it feels a much stronger force. And it turns out as you get close to a black hole, even something that is not very large can have a huge difference in forces between the far side of it and the near side of it. And what does that mean? That means you're getting a stretching force. It's like having a rubber band in your hand. You might think that if I'm pulling hard on one end and not as hard as another, it's not going to stretch it out. But you can imagine if I hold a rubber band in my hand, as a matter of fact, I have one on the desk, but I won't grab it. But if I pull with this hand, it stretches. If I pull with this hand, it stretches. If I pull with both hands, it stretches, right? It doesn't matter where I'm applying the force, the end result is a stretch. And the same thing would happen to you if you were falling into a black hole. And it turns out that even your height, even if you're only 6 feet tall, on average, or 2 meters tall, roughly, the difference in distance between your feet and your head becomes very, very important as you're falling into a normal black hole. Now, I won't go into this in detail just yet, but you're going to have a problem. The change in force is called a tide. This is where we get the word tide from. The moon is pulling on the Earth, and in fact, there's the near side of the Earth and the far side of the Earth from the moon. The near side's getting pulled harder than the far side, and the Earth stretches. And that's why we have 2 tides a day, because the Earth is being stretched. It's not just one side being pulled towards the moon, they're both being stretched. What happens here? Imagine you're standing on the surface of the Earth. Shouldn't be too much of a stretch of the imagination there. So if you're standing on the force of the Earth, basically you're being stretched apart by the tides of the Earth, because there's a force on your feet that's larger than the force on your head, and it's stretching you. And you can think of that as a force up and a force down. That's all a stretch is. You're 6,400 kilometers from the center of the Earth. So there's the force of gravity on you, but there's also this slight stretching effect. The slight stretching effect is incredibly small. It's only about a millionth of the same force that gravity is pulling on you. It's roughly the same as a drop of water, the addition of like a drop of water on your head or your feet. It's a very, very, very small stretching force. However, if I were to turn the Earth into a 3 solar mass black hole, that gets different. The sort of the minimum mass you can get for a black hole in an exploding star. Did you go over this, Mike? You were talking about supernovae?
You mentioned it briefly at the end of my talk.
Okay. The normal process of forming a black hole, it's when a star explodes and the core collapses, and due to all the craziness that goes on, you have sort of a minimum mass for a black hole. It's about 3 times the mass of the sun, roughly. A little bit less, but it doesn't matter. The point is, generally speaking, the smallest normal black hole you can get is about 3 times the mass of the sun. And when you calculate its size and you figure all this stuff out, you can determine what the force is, the stretching force is on you as you fall toward it. Well, if you're 6,400 kilometers away from it, the radius of the Earth, now remember, suddenly the Earth is gone, and now I'm replacing the Earth with a little black hole here in the center. That stretching force is quite suddenly half a gravity. Your head is feeling sort of a quarter of a gravity pull up, and your feet are feeling a quarter of a gravity pull down. This is on top of the fact that you're getting drawn down at a very rapid rate because the black hole is pulling on you very strongly. This is just the difference in the force your head and your feet feel. If you're 2,000 kilometers away, it's 18 gravities. That's a lot. That's 9 gravities up and 9 gravities down. That's at about the point where you black out. When a fighter pilot, airline pilots don't generally do this. If they're in a banking turn and they bank, right, the blood is pulled out of their head at about 9 gravities. That's when you black out. If you do a negative turn where you're actually feeling a force upward, you get your blood forced into your head. You get a red out. That happens at about 9 gravities when you black out, more or less. So when you're 2,000 kilometers from the black hole, you pass out. Turns out that's a blessing. At 1,000 kilometers, right about there, something like that. The differential force is 144 gravities, 72 gravities up, 72 gravities down. And it turns out it's roughly at that amount where your bones start to snap. When I was doing this talk for the first time, putting it together several years ago, I was trying to figure out when would your bones snap? What force do you need to take your femur, because your femur is your longest bone, that maximizes this differential force, something that's very long. How long did it take before it snapped? And I thought, well, I'll look up longitudinal stress fracture femur, and found it, and thought, somebody has the most nasty job ever, right? Here, hold this, right? And so it turns out that's where it snaps. That sucks. And so at this point, your body starts to disintegrate. At 100 kilometers, you're feeling 150,000 gravities. Notice how quickly these numbers are increasing. And when you're right outside the black hole, you have a differential force of 75 million times your weight up and 75 million times your weight down. So imagine hanging like an oil tanker from your feet. That's the force that you're feeling. It's close to that. This entire process takes less than a second. If you're starting at rest 6,000 kilometers from a black hole, 3 solar masses, you're sucked down so quickly that really thinking of this step by step is useless. It happens so rapidly, you're dead. Well, that is the second way a black hole can kill you. Certainly you can fall into a black hole, you can't get out, but then there's this technical word called spaghettification. This is an actual word that astronomers use. It's called that because as you're being pulled apart, you're being stretched, right? And you basically get turned into a long string of pasta that goes falling down into the black hole. Neil Tyson, the astronomer from Hayden Planetarium, likens it to being extruded from a tube of toothpaste, which I kind of liked. I like that analogy. Oops, there we go. So in fact, see if this works. Sometimes it does. There you go. And okay. Oh, there used to be a sound effect. The flash doesn't work well with PowerPoint, but there you go. So this is the second way you can be killed, is being before you even get to the point of no return, what's called the event horizon of the black hole, where the escape velocity is the speed of light. You're stretched out into pasta and you're dead. Sometimes. Get into that in a couple of minutes. It turns out there are more ways. And it's interesting that a lot of these are ways people don't think about. If you're near one when it's born, you are screwed. In fact, this is the scariest way in my opinion. 1960s, Cold War. We signed the Nuclear Test Ban Treaty with the Soviet Union. And it says that we will not test nuclear weapons. And it's a very strange way it's phrased. It says above the ground, below the ground, in the ocean, or above the atmosphere. And I'm thinking above the atmosphere is above the ground. But I have a feeling lawyers would say, well, that's out in space. It's not really above the ground. Whatever. So we both signed this treaty, and of course we trusted the Soviet Union implicitly, right? We knew they wouldn't test things. Yeah, right. We figured those dirty red commies, they're going to go out and try to blow up weapons in space, or maybe blow them up on the far side of the moon where we can't detect them. They put a couple of satellites in orbit around the moon to observe this thing, blow it up, they get all their data, and we're none the wiser. We never see it. So we put up these satellites called the Vela satellites. They just look like these weird, I don't know if that's an icosahedron or not, but they're basically covered with solar panels, and they've got gamma ray detectors in them. When you blow up a nuclear weapon, you get high energy light in the form of gamma rays out of them. And there's a signature to this type of blast. It sends out a very brief but very distinctive pulse of gamma rays. So we put these things up in pairs so that if the Soviets blew up a nuclear weapon, the two satellites would detect the gamma ray pulse. And because they're orbiting the Earth and there's a slight delay in the light travel time between the two, right? They're 8,000, 10,000 miles apart, something like that. There's a fraction of a second that the gamma rays will hit one satellite first and the next satellite. They could get a rough area of the sky where this thing would be, and they might be able to detect it. And the more of these things you put up, the more accurately you can determine where they are. And we put up several pairs of these. Now you're all sitting there looking at me. Is this making sense?
Sure.
Yes, Phil. No, Phil. Okay, don't be embarrassed. This stuff is strange, and I know it's a little weird, and so if it doesn't make sense, let me know. Because I'm going to get to the really serious stuff here in a couple of minutes. This is the easy stuff. It turns out that this works. You can actually sort of nail down the position to a really relatively narrow area of the sky and figure out what's going on. What happened was, Over the lifetime of this project, they detected 73 separate gamma ray events. Not a single one of these was tied to an absolute nuclear weapon. There was one they're not sure about. It blew up, I think, over the South Atlantic. And they don't know if that was a nuclear test or not. It was never pinned down. But everything else was not a nuclear weapon. And it turns out not only were they not nuclear weapons, not one was of this Earth. They were all coming from from space, I should say, not necessarily deep space. This whole story I won't go into because we're going to be starving by the end of this. We're going to be going to dinner. But this whole story is one of the coolest astronomy mysteries that there is. And there have been a dozen or so really interesting astronomical science mysteries over the past few centuries. This is one of the coolest. And one of the beauties of this thing is that we live right now at the time where we're getting the answers. For 30 years, these things were a huge mystery. We did not know what they were. We didn't know if they were coming from the solar system or nearby space or cosmological distances. People were saying, look, if these things can't be coming from too far away, if they're coming from a different galaxy, what the hell can be generating that kind of energy? When you calculate, we detected 100 gamma rays. We know how much energy they had. If this thing exploded and it was a spherical explosion, you can calculate how much total energy is in that explosion. And it's an insane amount of energy. It'd be like converting the sun into energy using equals mc squared. Crazy. You can't do that. So they can't be that far away. So they must be closer. But if they're closer, what are they? And the answer is we don't know. And you might expect that by looking where they are in the sky, you might be able to determine if they're far or near. For example, we're sitting in a room full of people. I'm sitting at one edge of this room. If I look in any other direction than behind me, than over here, I don't see people. So if I were to divide this up into wedges, the room, my view into wedges, I would see you guys here, and I'd see you guys here, and you guys here, and then nothing, 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 nothing. I can then deduce, or adduce, or reduce, or some sort of deuce, what the deuce, that I'm standing on one edge of this distribution of people, and that would be correct. If I were standing in the center and did that, statistically I would see people all around me, and I can say I'm standing in the center of this group of people. And you can do the same thing with gamma ray bursts. If they're coming from our galaxy, which is a big disk, and we're halfway out from the center, we should see more looking towards the center of the galaxy than we do looking away. And it turns out that's not true. We see them distributed all over the sky. So either they're coming from something very close or very far away, but they're not inside our galaxy, because if they were inside our galaxy, we'd see more in that direction. So just without even knowing much about them, you can kind of get an idea of where they are. The problem is you can't tell if they're really close or really far away. I won't go into a huge amount of details because it's complicated, but it's a cool story. I've written about it. You can find information about it. But basically, what it was determined is that these things are cosmological. They are happening at tremendously far distances away. And that, believe me, is good news. Because the amount of energy these things put out is unbelievable. They're called gamma ray bursts, or GRBs. They happen every day. There may be thousands of these things happening every day somewhere in the universe. But we're not seeing very many of them. We see on average one every 2 or 3 days. This was actually the first one that was seen by Hubble Space Telescope. I love this picture. I actually worked on this. This is a galaxy, a very faint galaxy. You can kind of see it as these two curls. I don't know why the hell I'm using this stupid thing when I'm standing right here. And so this curved thing, and here's the gamma ray burst, and you can see clearly that the burst itself is outshining that galaxy by a huge amount. Vast amounts of energy in these things. They only last a very brief amount of time. There are two different kinds. One only lasts for a fraction of a second. The other kind can last for minutes. But during that time, they are outshining their galaxy. They happen on average billions of light years away. And then we think of these two kinds, there are two different at this point, we're talking theory, no longer observation. This was all observation. We think there are two kinds. Well, we know there are two kinds because we know that they have two different properties. What is the engine behind them? We think we understand, kinda, but we're not completely sure. One is a hypernova, where you have a supernova. Some monster star with 100 times the mass of the sun explodes, and it forms a black hole. You're wondering why I was up here talking about all this crap. Forms a black hole in the center, and that generates a bunch of processes, which I'll get into in just a moment. And basically, you get a gamma ray burst. Another way is you have two neutron stars. objects that don't quite have the mass of a black hole, but they're very dense. They have roughly the mass of the sun, but they're not as small as a black hole. They're a few miles across. And they orbit each other, and over time, using Einstein's equations, you can calculate their orbits decay. This takes billions of years. And they spiral in, and when that mass gets together, it forms a black hole. The structure of the physics of the material can no longer support itself, collapses into a black hole, and you get a gamma ray burst again. I'm going over these things very rapidly and with not much detail. I will be happy to lecture you at length about this, or for $26 you could buy my book where I got a chapter about this. Scott loves it, saved his life, making that up. How much energy is in a gamma ray burst? What are we talking about? Well, we're talking about 10 to the 52 ergs. Astronomers are stupid. They use ergs. Nobody uses ergs. We use centimeters and grams and all these dumb units. And I think in them now, which is irritating because I've been using them all my life. That's 10 to the 45 joules, if you like that. For comparison, the sun is 10 to the 33 ergs per second. So this is 10 to the 19 times the sun's output. And if you calculate all that, you say, well, how much energy is the sun going to put out over its entire lifetime? It turns out that in a few seconds, a gamma ray burst puts out as much energy as the sun will in its lifetime, maybe even more, 10 times as much. Depends on the gamma ray burst. So you're talking about an object that lasts for a few seconds that puts out as much energy as the sun will in 10 billion years. Okay? Yeah. These things are scary. If you were to put the Earth in the path of one of these things, yeah, it's Bambi versus Godzilla. You're dead. You could take 100 billion Earths end to end, and they would one after the other poof, 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 poof. Right. So the Death Star is for wusses. This is the serious stuff. I actually like this because that's just the sun, compared to the Earth, and so multiply this by 10 billion, and that's what you get. The thing about gamma ray bursts, the reason we didn't think they could be cosmological is because we were thinking that stars blow up as a sphere. But then somebody said, well, wait a minute, what if it's not a sphere? What if you take all that energy of a supernova and channel it into a beam, like a laser beam? Now that laser beam we were playing with a minute ago is incredibly bright, but it has far less power than a light bulb. And yet I can blind somebody with that laser beam, and all you can do is maybe get a nasty burn from a light bulb. The reason is if you take all that energy and channel it into a narrow little beam, a little jet of energy, then you can get tremendous amount of energy in this thing. The total amount of energy doesn't have to be this vast thing because you're focusing it. And that also explains why we're not seeing as many of them as we expect. Because a lot of them, the beam's going in some other direction, we just don't see it. If I take my laser beam and point it over here, you're not going to see it. It's only when I'm pointing it right at you that you see that really bright light. So in fact, even though we're seeing one or two of these things a week or maybe even a day, there's probably hundreds of these that we're not because the beams are pointing in different directions. When I wrote my book, I alluded to this earlier when I was talking to you guys. What happens if you're near one of these things? How close do you have to be to a gamma ray burst before it becomes dangerous? And that's not an easy question to answer because it depends on what you mean by dangerous. I would suspect that wiping out the ozone layer of the Earth would count. Okay, just cause. I mean, you can fill in the blanks in your own head. And it turns out if you're roughly 7,000 or 8,000 light years away from a gamma ray burst, and you're looking right down the gullet of this thing, that's enough to just totally destroy the ozone layer of the Earth. So 7,500 light years seems like a pretty safe distance till you realize that the galaxy is 100,000 light years across. So 7,500 is actually fairly close. You have to get pretty close to these guys. You can ask yourself, on average, how often does one of these things go off? And then, have we been in the beam of one in our galaxy since the Earth formed? And the answer is, maybe. I love science. It turns out that the odds are 50-50. That in the 4.5 billion years, and yes, 4.5 billion years that the Earth's been around, don't tell any Arizona State senators if you saw that clip on YouTube of the one who was saying Earth is 6,000 years old. If you look at the Earth's lifespan, there's a 50-50 chance we've been near enough a gamma ray burst for it to hurt us. And in fact, the Ordovician extinction, where the trilobites all died, has signals in it that looks like it could have been from a gamma ray burst. Deep sea creatures tended to survive this mass extinction, whereas things that lived in shallow waters didn't. And there are other things that make people think that maybe, hard to say. We may never know. But that's how gamma ray bursts are dangerous. And in fact, that's why being near a black hole when it's born is dangerous. It's oh, excuse me. Let me say this slide. We have satellites up. One of them is called SWIFT. It's probably the most successful satellite NASA's ever built. Launched in November 2004, detects roughly 100 gamma ray bursts a year, and is working perfectly even after 5 years. This thing is a machine. It is a machine, but it was a phenomenal instrument to work with, and it was really exciting to see these things come in. It's detected the most distant gamma ray burst. It's detected the nearest gamma ray burst. It detects all kinds of crazy stuff. Things get a little funny. There's a supernova gamma ray burst connection. You need to have a star blow up to form these things, at least the massive kind, the kind that last for minutes at a time. And there are supernovae that we've seen in other galaxies that have gamma ray burst-like properties, but we haven't seen that intense blast from them. And it turns out maybe it was aimed kind of sort of at us and we were just nicking the edge of that beam. There could be other factors, but it turns out the nearest ones we've seen have been hundreds of millions of light years away. So still pretty far away. There have been some, that one that I showed you the picture of from Hubble was 9 billion light years away, I think. And had you been looking up in the sky with binoculars, you would have seen it. It was bright enough to see with binoculars. There was one a couple of years ago that had you just been looking up, you would have seen a whoop, blip of light. That's amazing. These things are billions of light years away, producing enough light that you could actually just look up and go, oh, what was that? The problem is when they get close by, I mentioned, what would happen if one were 7,500 light years away, wipe out the ozone layer. I calculated what would happen if one were 1,000 light years away, and it was a lot worse. There are all sorts of damage to it. And I thought, oh, screw this. What happens if it's 100 light years away? Woo! Let's see what happens. And then I got numbers I couldn't believe. I mean, literally, this is not an exaggeration, the hair in the back of my neck stood up. And I thought, this can't be right. So I worked the numbers backwards and got the same thing. So it wasn't an arithmetic error. I looked up some other papers and found that their numbers jibed with mine pretty well. If a gamma ray burst went off 100 light years from the Earth and we were right in the middle of the beam, it would be like detonating a 1 megaton nuclear bomb over every square kilometer of the Earth facing the beam. So that's tens of millions of hydrogen bombs blowing up all at once. It would scour the atmosphere off the Earth, it would boil the oceans, it would liquefy the continent. The amount of energy in these things is terrifying. Happily, there's nothing that close that can do this. And this is all because, and I go on about gamma ray bursts because I just love them, they're so cool. It's a black hole that powers them. And I'm going to go into that in a minute, how this works. I won't go into it here. But it's the black hole that forms the gamma ray burst itself. And that's why being near one, when a black hole forms, is the third way a black hole can kill you. So if you're near one when it's born, it can kill you. If you're near one when it's just living its life out, it can kill you. And it turns out if you're near one when it dies, it can kill you. Now, how does that work? Well, Brian, you were asking me about Hawking radiation. You get your wish. The next stuff I'm going to tell you is all baloney. In that I don't understand it to a level that I can explain it very clearly. This is fierce stuff. I read Hawking's paper about this. His seminal paper came out in the 1970s. I read the first paragraph and I went, yeah, okay, no problem. Read the second paragraph and went, yeah, I'll assume he's right. And then I got to the third paragraph and I was totally blown away. I had no idea what the hell he was talking about. Here's the idea. Space, and you've probably heard this, space is filled with virtual energy. It's kind of like a bank, where you can go to the bank, or you can go to a store or something like that, and if you steal $1, they may not notice. But if you steal $1 million, they're going to notice right away. The more you take, the quicker they're going to see it. The same sort of thing we think with quantum energy in space itself. Space is loaded with this energy. And some of it can spontaneously just appear. But the more energy that spontaneously appears, the quicker it has to go away, or else space might notice. It just, when you look at the equations of quantum mechanics, this makes sense. You can say, oh yeah, sure, you can borrow energy for a certain amount of time, but you have to give it back. And so there's energy sort of stored up in space around it. It turns out there's a lot. You've probably heard of the Casimir effect, which evidently demonstrates this. You take two metal plates and put them really near each other, and they're attracted to each other, and it has to do with how space is boiling with quantum foam. Ooh. Again, this is pushing the edges of my knowledge, so I can't go into too much detail here. I'm going to assume Hawking's right. Not a bad way to bet. A lot of people seem to have confirmed him. Here's the thing. Black holes aren't necessarily black. Let's look at a black hole. We'll look at close. We'll look near the event horizon. The event horizon is right where the speed of light is the escape velocity. Just past that, you can escape because you need a lot of energy, but you can get out. Just below it, you're gone. You're dead. That's it. There's nothing you can do. This is not really how this works. This is a model that Hawking proposed and people have backed up, but it's a good way of thinking of it. Imagine that there's suddenly a bit of energy out of this free energy in space. Some of this energy suddenly appears. One of the things that can happen is if there's enough energy in that, it can spontaneously, and I love this stuff because you're all going to like go, what the hell is he talking about? It can spontaneously turn into particles. Now you've all watched Star Trek. You know how warp drive works, right? You take antimatter and matter and you put them together and you get energy. That's true. It's the one thing Star Trek got right. In fact, that works in reverse. You can take energy, and if there's enough energy, you can create particles out of it. It's the same thing. You can create a matter particle and an antimatter particle. You put them together, they make energy. You pull the energy apart, you make matter. E equals mc squared. Energy and mass are two sides of the same coin. So imagine there's a flash of energy out of nowhere, and it forms two particles. One's matter and one's antimatter. It doesn't matter. That was not meant to be a pun, nor was it meant to be stupid. Well, they go shooting off in two different directions. My machine keeps falling asleep. Imagine this is right over the surface of a black hole. One of them might go into the black hole. The other one's going to go out. That one that falls in is gone, right? It falls into the black hole. But this other one may be able to shoot out. Now, if you're standing back from the black hole, you may say, well, it gained the mass of one particle and lost the mass of one particle, so nothing's really different. Except that that energy, the masses of those two particles, is now been taken from space. And according to the laws of quantum mechanics, that debt has to be paid. And the debt gets paid by the mass of the black hole itself. It actually loses that mass. And I asked a lot of black hole experts about this, and I say, I don't get this. Where does that mass come from? And they say all kinds of crazy stuff. One of them said, you're actually getting it from the energy of the black hole. When you're creating these particles, it's a negative energy. And I went, oh. And back away slowly kind of thing. I want to reinforce this. I'm not a stupid guy, but I'm not a genius, and I do not get this. There's a level to this where I have to say I don't understand. In fact, work is being done. And so I like to think of it that way. When you're doing work, you need to get energy goes into it someplace. The black hole itself is pulling these two particles apart. By pulling the two particles apart, it's giving one energy, taking the energy from another, but work is still being done. That means energy is being expended. That energy has to come from somewhere, and it comes from the mass of the black hole. Every step of that, I'm kind of like, okay. I can kind of get my hands around that. But the bottom line is that energy comes from the mass of the black hole itself. You're converting mass into energy, and the black hole loses mass. This is called Hawking radiation. One particle falls in, one particle leaves, and what you see is the black hole radiating mass. In the end, every time this happens, it's losing one subatomic particle's worth of mass. That's not a whole lot. When you're talking about the mass of the sun, it's a whole lot more than a subatomic particle. This is an incredibly slow process. But the net effect is that the black hole is radiating away its mass in the form of energy. If you look at the equations of it, it turns out that big black holes radiate very slowly, small black holes radiate very quickly. It has to do with the curvature of the event horizon and all kinds of crazy stuff. But it turns out it's very important how massive the black hole is, because this effect goes as the mass cubed. If you take a black hole that has a mass of 1 and one that has a mass of 2, the one that has a mass of 2 will actually lose energy 8 times slower, 1/8 as quickly as this one does. So as it's radiating away its mass and losing mass, it starts radiating away its mass quicker and quicker and quicker. And eventually, you get basically what's kind of an explosion. Now, a stellar black hole, something made out of a supernova that has the mass of the sun or more, will live a long time, 10 to the 67 years, which is far longer than the age of the universe, which is about 10 to the 11 years right now, 10 to the 10 years, excuse me. 10 to the 67 years is a vast amount of time. What's interesting, though, so we would not expect to see a stellar mass black hole evaporating now, because it's not going to happen for another 10 to the 67 years, really. However, there's an idea that little tiny black holes were made when the universe formed, that there were forces being tossed around, and they were so strong that they might have been able to compress not 3 solar masses of material, but maybe even smaller masses, like the mass of an asteroid, the mass of a mountain. And you'd get a black hole that's smaller than an atomic nucleus, but it's still a black hole, because you've squeezed this mass down to where the escape velocity is faster than light. These are called quantum black holes, they're called Hawking black holes, they're called mini black holes. They have all kinds of crazy names. But if you take one that has about 1 trillion kilograms, roughly the mass of a hill or a mountain, that was created when the universe formed 10 to the 10 years ago, then today it would, and you run through the equations, it would be totally evaporating right now. It would be losing the rest of its mass. And when it does that, it's basically an explosion. You see here, this is actual simulation. This thing gets brighter and brighter and brighter, and then kablam! When it gets down to about a ton, I think, it starts radiating away so quickly it acts like an explosion. And in less than a second, you're converting all that mass into energy. Turns out that when you do this, it's a pretty violent explosion, and it looks a lot like a gamma ray burst. And a lot of people thought when they were looking at gamma ray bursts, they were looking at quantum black holes exploding, but it turns out it's not. It's the wrong kind of signature of gamma rays. So the point is, a black hole evaporates. It takes a long time, billions of years, but it happens. And if you're near one, you're basically standing next to a huge explosion. And so clearly, that's the fourth way a black hole can kill you. If you're near one, when it does this and dies, it'll vaporize you. And that's kind of a cool thing to do. I'm standing on my own cord here. Got to be careful. That made no sense, right? I apologize. That's the best I can do.
So an exploding black hole is roughly equivalent to a gamma ray burst. There's no way to tell the difference between.
They kind of look the same. If you were just looking at one, you would see a flash of light. But in fact, when you measure the gamma rays coming in, you would see the way it gets brighter and dimmer is different. And plus, this is a much lower energy event than a gamma ray burst. Much, much, much lower. It still probably would dwarf all the nuclear weapons detonated on Earth. But compared to a gamma ray burst, this is a, snap of your fingers.
Have any events like that been observed?
Never. Which is too bad. Observing Hawking radiation is difficult. It's a very, very slow, low energy event. So it's still theoretical as far as I know.
One of the recent satellite earlier this year, last year, GLAST.
Yeah.
That's one of the things I was hoping to look for.
GLAST is, I'll get to GLAST in a minute. It's now called Fermi.
Right.
I still call it GLAST because I was working on GLAST when it was still GLAST, and they hadn't even started cutting metal on that thing yet. It's the Gamma Ray Large Area Space Telescope, and that's what GLAST stands for. And it's also a gamma ray. It has gamma ray detectors on it. It detects gamma ray bursts as well. That's its secondary mission. I'll get to its primary mission here in just a sec. Oh, and so I thought I'd already put that up. Evidently, my Mac keeps freezing on me, and I'm not sure why. I'll have to pay closer attention here. Okay.
What's the predicted frequency of those mini black holes?
Nobody knows. It depends on how many there are, and right now we know of 0. So the answer to your question is 0 plus or minus infinity. Sadly, it's because it's totally theoretical. We just don't know. And it turns out if they're not close enough, we won't see them. And honestly, I did that calculation and didn't put it in the book, and now I don't remember. But I calculated how far away you could detect it using Swift. It actually wasn't that hard of a calculation. I expected it to be really difficult, and it wasn't. But it has to be some light years away. And unless the universe is filled with quintillions of these things, the odds of seeing them are pretty low. So it really does depend. And since we don't know how many there could be quintillions of them, there could be octillions of them, nobody knows. So until we see one of these things, there's no way to know. Which is too bad, because it's cool.
So the theory that predicts they could be created in the Big Bang does not at the same time predict the frequency?
No, because you can show that the forces the forces that were being tossed around in the Big Bang were enough to do this, but we just don't know how many of them there might have been made by these forces. We just know that at some point in the history of the universe there were forces that existed like that. But it really depends on the asymmetries in it. If I were to suddenly take half the air of this room and move it over here, it would suddenly expand and there would be a force there. The same thing was kind of true in the Big Bang. It wasn't an even distribution of mass. There were slight changes, and so there were different. The forces that were working on it were different depending on where you were. That's why we can detect the cosmic microwave background at all. It looks like ripples in space-time. I won't go into that. But nobody knows. I don't think anybody really knows how that works. We may in a few years. The Europeans just launched a mission called Planck, which will measure the forces that were being tossed around in the Big Bang a lot more accurately than we know now. And so I don't know, but it's possible that it might be able to do that. I don't know what the kind of physics it's going to be doing, This isn't super duper my field. I've read about it, but sort of as a layman. So my knowledge of this isn't any better than anybody else's. And it's a hell of a lot worse than some people's. Okay, so moving on, the just passing through, as you saw, is another way. There's another obvious way. I mean, I've talked about some sort of unobvious ways. There's an obvious way a black hole can ruin your whole day, and that's if one passes through the solar system. And you know, Chesley Bonestell actually painted paintings about a white dwarf doing this. There have been plenty of stories. Eater is about this. Is it Greg Bear? There have been Benford, all these Gregs in science fiction. And so there are a lot of stories about black holes passing by and wiping out the solar system. How does that work? Well, it turns out very nicely, in fact. Now, I think maybe we should turn the lights off for this. And just because I want to do a sexy after-hours black hole, okay, here we go. This should work. As long as the screen is dark, you should be okay. Okay, this should open up. Yeah, there you go. So here's a black hole. Here's the sun with Venus, Earth, and Mars orbiting it. I just did that. I didn't put Mercury in there because it was too hard. This is actually a gravitational simulator that shows what happens if the black hole gets near enough the sun, and you see that's what we in astronomy call sucky. The planets all get tossed around. Mars actually gets into a temporary elliptical orbit. This is not the best mathematical simulator, but it gives you a good picture of what's going on.
What's the mass of the black hole?
3 times the mass of the sun. And I have it moving at some velocity, and it passes a certain distance from the sun. And it's fun because this thing isn't very good, but you can see that Mars gets near the sun. Now the sun goes past the black hole, and then Mars's orbit just changed because it got near the sun. And if you watch this thing for a while, it was actually a lot of fun to play with this. The calculations aren't terribly accurate. And so every time it does a calculation, it's using the previous calculation, and there are round-off errors. So it gets worse and worse as it goes on and on. But it's pretty fun to watch this. This one's bad.
Now, the books you were talking about, did the Earth just get catapulted out, or did we get sucked in?
Sometimes it gets sucked in. Sometimes it gets torn apart by the tidal forces. Let's see. There we go. Oh, wait a sec. There we go. There are all sorts of things. There is a story where the Earth gets sucked down into a black hole, but I think that was a short story I read a long time ago. I like this one a lot. I fiddled with a bunch of different scenarios. I started at the bottom because typically things move up with time. But in this one, Venus and the Earth get captured by the black hole. And their gravity affects each other. Mars gets tossed away, the sun gets tossed away. Venus and the Earth interact a few times. The black hole is extremely tiny on this scale. And so the Earth never gets sucked down by it. I don't know if this one actually does it. Eventually the Earth gets tossed away. But you can see as the sun gets farther away, that's bad. We kind of depend on the sun. And so the Earth would actually freeze solid, not to mention being really close to a black hole and torn apart, and all kinds of bad crap would go down.
So the Earth is actually getting very close to the black hole, but eventually will be catapulted away.
In this particular case, because Venus and the Earth are both drawn into the black hole, they interact gravitationally and their orbits keep changing, and then eventually the Earth gets ejected. In astronomy, there's the two-body problem, which is just simply you have two gravitationally bound objects and how they orbit each other. That's a solvable problem. With Newtonian mechanics, using Newton's equations, you can predict forever what these two things will be doing. If you introduce a third body into that, it turns out Newton's equations are not solvable. And so it really depends on exactly the masses and what direction they're all moving in. You have to do it on a case-by-case basis. You cannot predict to infinity what's going to happen to that system. And the same thing is here. Oh no, the Earth is actually, yay, Venus got ejected. I had that backwards. Okay, yay for us, Venus is gone. But it's impossible to predict what would happen in these cases. And so anytime you have the sun, the planets, and a massive object moving through the Earth, typically it's the lowest mass object that gets ejected out. It's just the way the equations work out. The black hole's very massive, the sun is very massive, the planets aren't. And so the planets just get scattered like pool balls if you just pushed on them. And so there's no good scenario here. If a black hole passes through the solar system, we're screwed. But in fact, how likely is that to happen? I have people who worry about this. They say, a black hole is so massive, you know, they're gonna destroy us. And it turns out the odds of this happening are very small. Over the lifetime of the galaxy, that's 10 billion years, there have probably not been 2 random stars that have passed so close to each other that something like this could happen. And black holes are much more rare than random stars. Over the lifetime of the sun, there's probably not been another star closer than about a light year to it. Just randomly. After it was born, it might have been born with a bunch of other stars near it. Back then, this type of scenario may have been a little more common. But since the sun left its nursery and has been orbiting the center of the galaxy, it's probably never gotten close, another star's never gotten close enough to affect us. Black holes are even more rare, so that it's going to be trillions of years before you might see a scenario like this. And by then, the sun is dead and gone anyway, so to hell with it, who cares? So really, you don't have to worry about this type of scenario. If you want to look in the long term, you know, 10 to the 50 years, 10 to the 100 years, yeah, these types of things happen commonly. But on the lifetime of the sun as it is now, no. So that brings us to number 6, which I believe, did it already do it? No, there we go. Be near them when they merge. People ask, what happens if you take 2 black holes and let them get close? What happens? I say, you get a bigger black hole. It's like 2 lumps of clay, right? You put them together, you get something bigger. In fact, it's not that simple. I'll show you this video. You can turn on the lights, or if you want, or is there a problem?
It's easier to see them.
Yeah, actually, you might probably keep them off. We think that at the center of every major galaxy, and that includes our own, there is a supermassive black hole, millions of times or even billions of times the mass of the sun. If 2 galaxies collide, these 2 black holes can orbit each other. And over time, they will get closer and closer and start to merge. One thing that Einstein predicted is if you take 2 massive objects and let them circle around each other and merge, they will create ripples in space-time, similar to if you take a rock and throw it in a pond and the surface of the pond ripples. These are not sound waves or anything like this. This is an expansion and a contraction of space itself. Space, if you had a yardstick, would expand and contract and expand and contract. It has to do with gravitational radiation and all this crazy stuff that Einstein thought of. But it turns out we've experimentally seen this happen. 2 neutron stars are orbiting each other, and their orbits are decaying exactly as Einstein predicted, if this idea is correct, that space itself is a thing. And if you have 2 massive objects that circle around it and they create these ripples, it's called gravitational radiation. And Hulse and Taylor are 2 astronomers. They won the Nobel Prize for showing that the orbits of these 2 neutron stars are decaying exactly on the line that Einstein predicted. It was like one of these get a chill down your spine moment when you see it. As a scientist, you go, oh yeah, that rocks. Einstein was right on the money. These boneheads who say, Einstein's wrong. You say, yeah, get back to me when you predict gravitational radiation and we'll talk. So basically that's what's going on. You're expanding and compressing space-time itself. Well, what happens when you do that? Well, when you do that, you get these ripples. And these ripples are sort of an expansion and contraction of space-time, sort of like when I'm talking and I'm compressing and rarefacting the air as my sound waves are moving out to you. The space itself is doing that. I have seen different calculations of this. The most recent one says it's not as bad as I thought, but I don't know if it's accurate or not. But it's possible that if you're within a certain distance of 2 supermassive black holes colliding, space will expand by a factor of 2 and compress by a factor of 2, which means you will suddenly become 10 feet tall and then shrink down to 2.5 feet tall, and then be 10 feet tall and be 2.5 feet tall over and over again, basically as these ripples move past you. And by the way, these ripples move past you at the speed of light. So you're going like that, you know, 1,000,000 times, and you're basically plasma at that point. You're goo. So this will kill you.
It's fairly out of my realm of being able to understand it, but isn't
Me too.
all of space? It's almost like you're adjusting height and width relative to the world or to the universe around you. So would everything sort of be?
You wouldn't notice.
No,
Yeah,
I guess, yeah.
Yeah.
Technically, you wouldn't even notice.
It turns out it's a radial effect. So as these things are moving past you, you're compressing this way, but not so much this way. Sort of like ripples in a pond as they move past you. You feel the effect. I think, how do I explain this?
On the line of the explosion, you would move in that direction?
Yeah, sort of. I mean, as the wave moves past you, you feel sort of that force backwards, but not to the side. there's a slight force to the side because you're feeling the curved parts of the wave are hitting you as well. So there's sort of a force that's pushing you this way with a wave. But mostly it's radial. And so there's this compression this way, but not so much this way. And again, we're right at the edge of what I understand with this stuff. It's very complicated.
Because I think it's one actually, isn't there a chance that we wouldn't even notice it because it's space itself
In time,
is with stretching and that.
Yeah, but the wave doesn't hit everything all at once.
Yeah.
If it hit everything simultaneously.
Oh, it's like-
And this gets weaker with distance
It's like
too.
it hits you,
The amplitude shrinks.
stuff hasn't been shrinking and contracting behind you yet, so.
Yeah, imagine if the wave had a wavelength of the distance between you and me, you would be compressed while I'm being expanded, so I would see that. If everything were being expanded at the same rate, then I don't know if you'd notice it. People argue about that all the time.
But if space is stretching that way, then how does light propagate through it? Like, wouldn't that, isn't?
I don't know. That would be the technical
Can we
explanation.
quote you on that?
No, I don't know. I don't know.
Always wondered about that.
Again, this is sort of pushing the boundaries of how I understand all this. As I understand it, this is what would happen. And you can trust me, I'm a scientist.
Do we see artifacts that we think are related to this having happened historically, like the way a shock wave passing through a star, through gas creates star clusters, and you could look at that and say that there was
This is an extremely weak effect. Extremely weak, unless you're talking about supermassive black holes. If you have two regular black holes collide, you still get this, but it's much weaker. With neutron stars, you get it as well. I can semi-answer that question by saying that we are building detectors to look for this. They're called gravity wave detectors. There's one on Earth called LIGO, the Laser Interferometry Gravitational Observatory, I believe is what it is. It's basically a giant L. There's one end of it's in Washington, another end of it's in Louisiana. There are these long, straight, evacuated pipes underground with basically with detectors at each end. And they beam laser beams at each other. When the laser beams interfere with each other, you can measure precisely the distance between them. If a gravity wave passes through the Earth, then the distance between the two lasers should change, and that interference pattern should change, and you can measure it. And they're getting, the problem is, with its current state of the art, we're not quite able to detect this yet. If you go to the LIGO website, they have this neat graph which shows you where they are in being able to detect things, and everything is still below that line. But that line keeps getting lower and lower as they figure stuff out and get these detectors more sensitive. And we are right on the edge of getting this. And I'm thinking it could be like in a couple of years they may get their first real detection of a gravity wave of these two laser beams going vibrating. The Europeans and the European Space Agency and NASA were going to collaborate and build this thing called LISA, which is the Laser Interferometry Space Array. It's these three wagon wheels. They each have lasers. They talk to each other with laser beams, and there are test masses in these things that weigh about 1 kilogram. If a gravity wave passes through these things, the test masses will wiggle a little bit. The amount they wiggle is a petameter. So it's a thousandth of a trillionth of a meter, I think. So it's a millionth of a nanometer if I've got it might be a femtometer. It's one of these crazy prefixes, right? Prefaces, I suppose that would be. And I remember reading about this and I said, this is Star Trek technology. And it turns out, no, you can do this. You separate these guys by enough and they become very sensitive because the farther apart they are, the less you have to move the laser beams to actually detect all this. And they say that we can build this. We almost have the technology now. It's been delayed and delayed and delayed. The last time I did this slide, actually, it had already slipped past 2011. At this point, I don't think it's ever going to get built, which is too bad because it's pretty cool, but it would be very expensive. And it really is too bad because this is a pretty nifty idea. So we've detected gravity waves indirectly because of the decay of neutron stars, but we've never detected them directly using one of these gravity wave detectors. That will be a huge day when they detect it. It'll be very cool. Finally, and I love saying finally because actually there's a bit to talk about here, but I'll go quickly because I'm running late. You can be fried by the light. One of the biggest ironies of black holes is that you expect they're the darkest objects in the universe, right? You shine a flashlight into it and down it goes. But in fact, black holes are also the brightest objects in the universe. Well, how does that work? In the 1960s, there was observations of the star HD 226868. It's an O-type supergiant. It's one of the most massive type stars known. It's like 40 times the mass of the sun, something 20 times the mass of the sun. The more massive a star is, the brighter it is. And they were observing this star with an X-ray telescope, Uhuru, the first X-ray telescope that was launched in the 1970s, I think. I don't know the exact date. Doesn't matter. And the thing is, this star was blasting out X-rays. And we know that O stars are bright. We know they put out some X-rays. But it was a huge amount of X-rays. It was actually 100,000 times the energy of the sun. And this thing should not have been putting out anywhere near that amount of X-rays, not even close. What the hell's going on? Well, then they started observing it more carefully, and they got a Doppler shift on it. And they found out that this star is evidently orbiting an object which cannot be seen. And we realized, oh, it's orbiting a black hole. The black hole only is a fraction of the mass of the star, but because it's invisible, we don't see it, and that we can detect the star's motion around it. If you were to get close to it, you would see something like this. The black hole, if you actually do all the angular momentum arguments, which is, believe me, very fierce. I took a class in this, and I dropped out. I was auditing it because I wasn't stupid enough to take it for a grade. I didn't need it. It was extremely complicated equations, and because I had a full load of classes, I couldn't spend the time I needed to learn all this stuff. Kind of regretting that now because it was pretty awesome. But you can work out the equations. You can find out that if it's close enough, it can actually draw material off the star, which then spirals into the black hole, and it forms this disk called an accretion disk. And this material swirls around the black hole, and as you get closer and closer, it's going faster and faster and swirling around, swirling around, swirling around. Right near the black hole, the difference in orbital speeds can be huge. It's kind of like tides. You can be right above the event horizon and then 1 inch farther out. And these two velocities can be different by thousands or hundreds of thousands of miles an hour. So particles are rubbing against each other very fiercely. And what happens when you rub things together, right? They get hot. In the meantime, there are magnetic fields going on. There are all sorts of crazy forces. It's a witch's brew going on near the center of this black hole. And that all acts to heat this material up. It gets to millions of degrees. And when something is radiating at millions of degrees, it gives off X-rays. So that's where you're getting X-rays from. It's not from the black hole itself, it's the stuff falling in. You get this disk of material, that stuff gets hot, and that's why you see this stuff. The magnetic fields also can form these spiraled cones that come out of the poles of the black hole. And that's where the jets of gamma ray bursts come from. The magnetic fields kind of wind up, and if you've ever taken a bunch of strings and attach them to something and spin it, right, the strings get all tangled up and knotted up. That's sort of what's happening here. The magnetic fields get tied up. They form a cone that comes out of the poles of the black hole. Material can be forced up that stuff at extremely high energies. And so when the black hole forms, it forms these beams of material that last for a few seconds while matter is falling into the black hole. But if a black hole's near a star, it has a constant food source. And so it's constantly eating, constantly forming an accretion disk, constantly forming these beams. Well, if you go outside at night, tonight, to a dark site in the summer, you get to see this. It's the Milky Way. I will use the laser pointer here. This is the center of the galaxy. You can see some of the nebulae and star clusters. Sagittarius is in here someplace. I can't quite identify it. I'm not sure which stars are which, but right in here is the center of the galaxy. That's what it looks like through an optical telescope. If you take something like Keck, the 10-meter infrared telescopes, and look at it, you can see stars. And the stars are moving over time. You can see this counter clicking, 2005, 2006. And as they observe these stars in the center of the galaxy, these stars are all orbiting a mass which is right here at this center star. I'll repeat it. I think it just repeats here. There we go. And you can see as they approach this thing, they move faster. Right? As they get away, they move slower. But all these orbits are centered on this object. Because we see these stars, these are actual observations, by the way. This is not an animation. This is actual observations stacked up using this telescope. When you observe all these stars and get all these orbits, you can calculate the mass of that object. And it turns out the mass of that object is 4 million times the mass of the sun. It's clearly not a star. There's no star with that kind of mass. It's not a cluster of stars, because then the cluster would still have to have a total mass of 4 million solar masses. And if you take 4 million stars and stick them together, they're going to be kind of obvious hanging out together. It's going to be glowing like 4 million suns. And yet we see nothing. Thinking black hole, right? And it turns out that's exactly what we're seeing here. Here's a map of that. Right here is the black hole. You can map out all these stars, and they map them out over time. This was a phenomenal observation done by Andrea Ghez and some other folks. And I mentioned her name specifically because she's cool. I met her last year. And also, she's a chick. We were talking about women, and I use that term sarcastically. She's actually a brilliant scientist and is doing really good work with this stuff. And she didn't necessarily discover the black hole, but she kind of threw a rope around it and said, this is what it is. And so it's very, very cool. If you were to approach that black hole, what would it look like? Well, here's a galaxy. You zoom into the center, and you get past all this sort of hubbub at the center. And if you have one of these supermassive black holes, in the center of our galaxy, there's nothing there. There are stars, there's some gas, but that black hole's not actively feeding. Our black hole is quiet. But if there's a lot of gas and dust and junk swirling around this black hole, you can get a huge accretion disk. It can be light years across. And it gets millions of degrees hot. And so it blasts out energy. And it would look something like this. You get a little cutaway here, but the black hole's right at the center. You have a huge amount of material swirling around it. It's being squeezed flat by the tides of the black hole. That's a little bit complicated. But near the center, it's squeezed flat. As you get out towards the edges, that force is less. And since the disk is hot, it puffs up like a hot air balloon. So it kind of looks like a donut that you've squeezed around in the middle and let it puff out at the edges. And you can form these beams of energy coming out. Well, these beams are powerful. You can detect them in radio waves. As these things slam into intergalactic gas, they slow down and billow up into these gorgeous Q-tips of energy. And these are actually radio maps of interstellar gas. We're talking objects that are a long way off. This one's 600 million light years away. These jets of gas are actually tens of thousands or hundreds of thousands of light years long. In this one, M87, this is a relatively nearby galaxy. We might even get a look at this one tomorrow night if we go to Wyro. It's a pretty bright galaxy. You won't see the jet, but that jet's aimed relatively close to us, and so we can see it. It looks like that. I've observed it. It's actually really cool. You don't want to be near this. There's a galaxy that was this galaxy 3C21, third Cambridge catalog of radio objects, and it's the 21st object in it. This is an actual observation in X-rays and optical light by, I think, Hubble and the Chandra X-ray telescope. This is the galaxy here. This is the main galaxy. There is a jet of material that's slamming into this companion galaxy and getting all disturbed. This is a drawing of what it might look like to give you a better idea. I guess I can't. Here, can I lift that up for you to make it easier to see? No? Okay. That's a joke because I'm tilting the. Wake up, folks. That's the. Yeah, they don't get any funnier than that. So this thing is probably blasting this nearby galaxy with X-rays and gamma rays and all kinds of disastrous energies. And if there's any living being in that galaxy, yeah, not so much anymore. They're getting lethal doses of radiation from this nearby supermassive black hole. We're far enough away that it's not a big deal. Our galaxy is quiet because there's nothing feeding our black hole. It's just kind of sitting there. If something were to start feeding it, this could happen. The good news is the jets would probably go out of the galaxy and not towards us. And even if they move towards us, there's enough junk, gas, and dust between us and it that it's probably not a big deal. It probably wouldn't kill us, probably. Don't know. In GLAST, now called Fermi, it was renamed when it went into orbit. The Gamma Ray Large Area Space Telescope, launched in June 2008, has been performing very well, has gamma rays on it, and it can detect these types of galaxies called active galaxies that are actively eating material and very active in energy, shooting these beams out. It is actually already detecting thousands of galaxies. As material flows into the disk is not always stable. It can fall apart, you can get clumps, and so these things are constantly I shouldn't use the word constantly. The amount of energy we see from them is not constant. They get brighter, they get dimmer. Sometimes you can see that in optical light, you can see it in radio waves, and by looking at them over all these different wavelengths, we can understand how these black holes are feeding.